SwayamPrabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 25. We were talking about the temperature distribution of a sand molding, and we on one side of the molding the temperature boundary condition was that equal to the freezing temperature of the material, the other side it was open to the ambient air, and we were trying to decipher what would be the distribution of theta per se with respect to time and temperature. So for that we had actually done the singularity variable analysis yesterday, through which we got a variable eta and then tried to convert the one dimensional heat transfer problem in time and space to the variable eta. Okay, and so what we found out what was this expression d theta by d eta equals y equals c2 e to the power of minus eta square. Just writing that back here, d theta by d eta equals c2 e to the power of minus eta square, meaning thereby that theta can be represented as, if we just integrate theta, d theta, so it can be represented as integral 0 to eta e to the power of minus z square dz plus c1. And let us now decipher what is c2 and c1 through the normal boundary conditions. So if supposing eta, which is actually x by twice root alpha t, for x tending to 0 also becomes 0, so the eta tends to 0 here, and in that event theta would be actually equal to c1, and at the boundary of the mold where x is 0, you already know that the theta has been defined as the freezing temperature theta f. If you may just recall, this mold was the something like a sand mold. Okay, on one side of it the boundary was corresponding to the start of x equal to 0, and as x would proceed all the way to infinity, at x equal to infinity you would assume theta to be equal to theta infinity, and then there is ambient air which would be all round this particular mold. Okay, so theta equal to theta f here, and the other thing would correspond to, so eventually when for a large amount of time the theta would tend to be equal to theta 0 at x equal to infinity, meaning thereby that it is always sort of, it is actually equal to the room temperature. Obviously it is a very large distance away, and so it should be equal to the ambient temperature. So this is theta 0. Okay, so having said that, now let us now try to evaluate theta f becomes equal to c1 corresponding to eta equal to 0 at this particular phase. Theta equal to theta f here, and therefore theta can be represented as c2 integral 0 to eta e to the power of minus z square dz plus theta f. And let us look at the case when eta is infinity, that means corresponding to x tending to infinity, the theta becomes equal to theta 0. So you have theta 0 here, this is c2 integral 0 to infinity e to the power of minus zeta square d zeta plus theta f, and this is actually a numerical integral whose value is estimated as root of pi by 2. So that is how you can estimate what is going to be the c2 value. For in this particular case the c2 times of root pi by 2 happens to be equal to theta 0 minus theta freezing, and so the c2 would come out to be equal to twice pi root pi theta 0 minus theta freezing. So having found out what is c2 and what is c1 through these two equations, I substitute this back into the final form of the equation here, which we call 7, and try to find out what is the distribution of theta. So the theta then becomes equal to c2, just let us write the equation once more, 0 to eta e to the power of minus zeta square d zeta plus theta freezing, which is actually the temperature boundary condition along the face of the mold, and C2 here becomes equal to, again if you just look back, C2 becomes equal to 2 by root pi theta 0 minus theta f. So, twice by root pi theta 0 minus theta f times of integral 0 to eta e to the power of minus zeta square del zeta plus theta f. So, that is how theta is represented, or in other words, if I just were to add and delete theta 0. So, basically let us say we add and delete theta 0 here. So, I would have a much simpler form of the expression as theta 0 plus theta f minus theta 0 times of 1 minus twice by root pi integral 0 to eta e to the power of minus zeta square zeta d zeta, and this is nothing but the error function of the term eta, okay, and eta basically is nothing but so this is a numerical integral. So, eta is basically nothing but x by twice root alpha t, and so therefore, the value of theta comes out to be equal to theta 0 plus theta f minus theta 0 times of 1 minus the error function of x by root twice root alpha t. So, that is how I would like to finally express the theta, calling it equation 8, and then this is the only case where I have, in the interest of just detailed knowledge, I have tried to prove what is the value of the theta. You will have to understand the all other conditions that are trying to happen, including the condition where there is a resistance at the the mold wall because of the thin air film developing between the liquid metal and the mold, or in a case when there is a liquid to liquid or a solid to solid complete welding because of a solid mold. The only things which vary there are the boundary conditions. So, we will try to sort of evaluate at various boundary conditions and try to decipher what is going to be the heat transfer equation in those cases. Unless there is curvature, etc., these are the normal modalities which are followed. So, that is how you basically represents the temperature distribution function of the mold as a function of distance, and here it is probably prudent for me to define the error function. So, error function of a function z can be written down as a series as twice by root pi times of z minus z cube by 3 times of 1 factorial plus z5 by 5 times of 2 factorial plus so on and so forth. So, this is from common knowledge of mathematics. I am not going to go into the details of all this, but just to represent it, because we need these and illustrations of these to sort of prove the various boundary conditions, etc. And then also the error function of z, as you know, can be written down as the integral twice by root pi 0 to z e to the power of minus x square dx, and obviously the value of this integral of this numerical integral is commonly available in tables through which we would like to sort of illustrate or actually try to find out what are the real times of solidification, etc., based on this distribution of theta, etc. So, also that d by dz of this error function should be able to get represented as twice by root pi e to the power of minus z square. So, these are some things, we call it equation 9, equation 10 and equation 11 is some of the basic mathematical forms of the error function that we would like to investigate, or we would like to use basically later on from our analysis point of view, and we already know how this error function is related with respect to theta as a function of x. So, this is in a nutshell the summary of the whole form of representation of theta. So, theta x is now the temperature at a distance x from the mold face at an instance t, and alpha is the thermal diffusivity, which is normally given by thermal conductivity K by rho C. That is how it was defined in the heat transfer equation. K is the thermal conductivity, rho is the density of the liquid metal, and C is the specific heat capacity, density of the mold, I am sorry, and C is the specific heat capacity of the mold as well. This temperature distribution, mind you, is in the mold. So, it is actually the sand properties that we are evaluating here while doing the theta distribution within the sand mold, and therefore, now you already know that the rate of heat flow which would happen from the metal to the mold would really depend on minus K, the thermal conductivity, times the area of the mold interface with respect to the liquid metal, times of this difference or the gradient of temperature with respect to x. So this d theta by dx is something that we have to look at the boundary x equal to 0. So you already know that the sand mold, as I had illustrated earlier, had a boundary where the theta value that was there was corresponding to the freezing temperature, and the heat transfer that was happening was typically in this direction across the area of the mold metal interface. So the amount of heat quantity, now heat rate q dot, that is emanated from the, obviously the metal which is at a higher temperature to the mold, is actually dependent on minus Ka d theta x by dx at x equal to 0. Okay. At x equal to 0, and so that is how you basically try to decipher the q dot or the rate of heat transfer. So having said that, now the obvious idea that would come into picture is how to sort of calculate what is this q dot, okay, and try to then illustrate everything in terms of temperatures, theta f, theta 0, so on and so forth. So we have to somehow now be able to find out mathematically what is this d theta x by dx from this expression theta x, so that I should be able to calculate what is the rate of heat flow. So let us do that. So here you have on one side dq by dt, which is actually equal to minus Ka d theta x by dx from the simple Fourier's law at x equal to 0, and the theta x as a function of x has been given out as theta 0 times of theta f minus theta 0 times of 1 minus the error function of x divided by twice root of alpha t, and therefore the del theta x by del x here comes out to be equal to theta f minus theta 0 with the minus sign, of course, times of twice root of pi times of the 1 by root alpha t e to the power of minus x by twice root alpha t whole square. Okay. So that is how you calculate the error function, because already I have defined d by dz of the error function of z as equal to 2 by root of pi times of e to the power of minus z square. Okay. So in this case z, of course, is x by twice root alpha t, and so the d by dz of the error function of x by twice root alpha t would actually become twice by root pi times of e to the power of minus x by twice root alpha t square times of the derivative x by 2 root alpha t. So it is basically 1 by twice root alpha t. So having said that, okay, so that is how we have substituted this value right about here. So let us now look at what really that would be. So this is actually the 2 goes off here, and we are left with at x equal to 0, if we want to calculate the del theta x by del x at x equal to 0, that becomes equal to theta 0 minus theta f. So the minus is taken inside, times of 1 by root of pi alpha t times of e to the power of 0, which is actually can be again further written as theta 0 minus theta f by pi alpha t to the power of half. So that is how dx d theta x by dx, the temperature gradient at x equal to 0, is defined, and therefore the dq by dt that I was talking about is minus k times of a times of theta 0 minus theta f divided by again the pi alpha t whole under the root. In other words, it can be written down as k times of theta f minus theta 0 divided by pi alpha t to the power of half. So that is how the dq by dt at x equal to 0 is going to be defined. So having said that, now the total quantity of heat flow across the mold face up to a certain time t0 is q T0, the total amount of heat, is the integral from 0 to let us say time T0 of this q dot del q by del T dt. Okay. So, if I really were to put this integral here to solve, the q0 had earlier, the q dot had earlier come out to be Ka times of theta f minus theta 0 by root of twice or root of pi alpha t dt. So, this value would then actually be equal to twice Ka theta f minus theta 0 divided by root of pi alpha times of root T0. Okay. So, t to the power of minus half, the integral of that is minus 1 by twice t to the power of half again. So, minus 1 by 2 t to the power of half again. So, that is how you calculate this integral. Okay. So, that is how your total heat from time 0 to T0 across the mold face would actually flow. Okay. Next, calculate the heat that the liquid metal would reject in order to solidify. So, if the liquid metal has latent heat L, a specific heat capacity Cm and a density rho m, then the heat rejected by the liquid metal converting to solid can be written down as rho m times of V, obviously the mass times of the mass that has been converted into solid times of the latent heat L, which goes undetected because there is a phase change, times of Cm, the specific heat capacity of the metal from the pouring temperature to the freezing temperature. So, you assume that the solid that has been formulated is at the theta freezing point or theta freezing temperature, and the pouring temperature is different than the freezing temperature, meaning thereby that you are superheating the material in order to introduce into the molds, just that the time of solidification can be delayed a little bit and you do not have any problems in filling the mold with the reverse flow of the riser side. So, in that situation you are having the total amount of heat reject Qr equals to rho m V times of L plus Cm theta p minus theta f. So, having said that, now if I incorporate this into our expression earlier, so the total amount of heat rejected should be the total the heat that flows out. So, we have an equation Ka times of theta f minus theta 0 times of root pi alpha times of root T0, that is the amount of time that this heat would take for translating. Okay. So, this I actually call T0 at this point, and I will let you know what exactly this value means, should be equal to rho mv L plus Cm theta p minus theta f. Okay. So, this time T0 is nothing but the total amount of time that the liquid metal would need to solidify, and so therefore, we can record this as the solidification time. Okay. So, this is how you in principle calculate the solidification time of a certain mass of liquid getting converted into solid because of the heat transfer across the mold wall, assuming that there is a temperature distribution with a function of x starting at the mold wall onwards into the particular sand mold. So, having said that, I think I have arrived at a sufficient justification for you to be able to estimate. Now, we will look at practical problems, but for that we need to probably break here and then go back into the next module later on. Thank you so much.